Okay, good morning, everyone. As well, we are the colleague from ONERA and myself. I'm from the German Border Police, and Philippe is from the French Institute of ONERA, and we are the practical part of the project. And we want to show some ideas and some solutions here for the practical work in our daily duties and our daily challenge. Okay.
Oh, maybe just one comment before starting, because there's also a colleague on this slide, so Axel Garcia, Jean-Philippe Molinier, Marianne Bourret, so all of them from ONERA side are now involved in experiment for OTH applications, so we are not able to attend, but there are the specialists actually on that topic, and Jens is
also here.
Yeah, so.
Okay. So we give you some information in the outline here. At first, we show you some information about the OTH radar operations, which is used from the French colleagues, and which gives you some information about the principles of operation, the TID impact on OTH radar systems performance, and then the second part here is to show you some principle in operation of data direction finding systems, which is used from the GFP, and then we show you some expectation from the TID FORS forecast, what we think that could be important for the future work. So, Philippe.
Okay, so some of you I think are well aware of what is an OTH radar. So for the others, just here something which explain how such kind of system can operate. So Skywave over the horizon radar use the reflective properties of the HF band, electromagnetic wave, to reflect in the ionosphere. And this allows us to use the ionosphere somehow as a secondary mirror, and then by radar signal processing, we can extract and detect not only clutter but also moving targets thanks to the Doppler analysis of the returns from the area under scope. So it allows to monitor areas which are beyond the classical line of sight of radar. So this is a very powerful capability. Powerful. There's also some drawbacks, of course, but it's powerful and it was primarily designed especially for early warning capability, especially for ballistic missile launch and such kind of big big objects. And then in the history of OTH radars, there was somehow it was somehow abandoned for some years, and now it come back on the stage, and we saw, for instance, on the Canadian side, US side, some interest in such kind of technology, especially to monitor very northern areas where some activity takes place, let's say, and this is something which is for our understanding quite interesting and for future applications. In terms of systems, so during the T-FORS study, we use an OTH radar, so not really as an OTH radar. We use it more as a beacon, so it's well, okay. And we use the one designed by ONERA, so it's not an operational system. It's only for study and yes, to support system assessment. So it's a monostatic OTH radar. So it means that both transmitters and receiver are on the same location. There's a little bit less than 300 beacon antenna. It's which are deployed over three arms. All of the electronic system, transmitter, and so on are in tunnels, in underground tunnels. Sorry. We are now moving to some sort of fully digital array. So all the transmitter side is done yet. We are still working on the receiver parts. It has a 360 degrees coverage, and we can control the beam in azimuth and elevation. And it's located not far from ONERA main office, so 80 kilometers west from Paris. In terms of principle of operation, so for each mission, the trade-off is to select the good frequency, and this is done, of course, according to frequency allocation. So we have to follow some rules, like every active system. We have to cope also with noise and interference on the receiver side. So in the case of Nostradamus, we have to analyze what is the environment, and for all the application, especially for bistatic application, we do the same at the receiver node locations. We can also adjust the frequency so to cope with specific targets. So in that domain of frequency, the wavelength makes the signature of the target very dependent on the length of the targets. So depending on what you are looking for, you could also try to consider also the wavelength in your in the mission preparation, so to adjust, so to select the best frequency which for the detection of specific targets. Of course, a mission is defined by the area to monitor. So in terms of beam steering, azimuth and elevation angles, and all of that for this last part depends on the propagation environment status. So in that case, the ionosphere. So it's two illustrations just to show you what are the impacts. So on the left hand side, it's a result from ray tracing. So with that, you can estimate at what range you will be able what range you will be able to illuminate. And this is done thanks to models, but also thanks to soundings. So it can be horizontal soundings, or in that case, on the right hand side, there's just an illustration of what we perform with Nostradamus during the operation. So it's an oblique sounding. So we are able to map, let's say, the area for the ionosphere, but this has to be done for every frequency and every elevation. So in terms of system and system application, it takes time. And as a matter of fact, when you consider resource management, this has to be considered. And any kind of contribution from system, from modelization forecast, could have an impact on this part. So we can. The idea is really to have the more time for the mission and not for the calibration. In terms of TID impact on OTHR, so these are really rough ideas, but the first one is about radar availability. Availability is since the OTH radar rely on the condition of the ionosphere. And in the case of TID, this could impact the attenuation. So we have to take into account these factors in the mission planning, for instance, and so to be able to say, okay, yes or no, we can illuminate in that direction, and what will be the performance, and so on. So it's something we have to consider when we prepare our missions. And the second one is about radar accuracy, as skywave signals are deflected by TID, which results in coordinate registration errors. So this is also something we have to consider, and this. From our perspective, these two impacts might be the more important one for OTH mission. So now we move on to the HF direction finding system.
Okay. Okay, thank you, Philippe, for the change. Yes, I will show you some principles for high data direction finding. You can say this systems are all over the world, and some principal topics. Now, we use in Swisttal, it's a small village, 25 kilometers in the west of Cologne, a high sensitive antenna system. Only it's produced from the firma Plat. I think in the last century, and it's a root antenna installation. You can see it on the picture here on this. Oh, here. Two cycles with 16 and 80 element concentric cycles. And the out cycles, the large antennas here are for the frequency from 1.6 megahertz to 7 megahertz. And the inner circle is used for the frequency from 7 megahertz to 30 megahertz. In the middle of the center here, you can see it here on the Google Maps or Google Earth view. Is one antenna more. This antenna is produced only for the receiver. You can see the noise, so you can see the signal online, and this antenna is also used to monitor the signal in an online process. So where we get the direction from the transmitter, you see here in a very old picture here on this year. I think it's from 1919. It's a very old picture, but it shows you the principal function of an Adcock system. And this antenna system is also an Adcock system produced from the Plat company from Hamburg. You see here if the wave is coming, for example, here from this to the electromagnetic or the geomagnetic wave front is coming in from this side here. You have more voltage level as on the other side, and this difference can show you the direction where the signal is coming in. So you can see this antennas, which works in this principle in very, very different ways. I show you here a little one. You can see this little one system on every airport on the tower, which used for the VHF and UHF signals for aeroplanes, for direction finding for aeroplanes, and so on. Okay. You can see in an example, it's a very old example here from the direction finding system. Here on the screen here in this, you can see where the signal is coming from. We see here 360 degrees, and for example. The signal come here from 45 degrees. You have here a lightning in the screen, and the receiver is able to cap one of the side, and the other side shows you where the signal is coming on. You can see it here on this side. For example, the signal came from here from 45 degrees. And so the transceiver, and the direction finding system is able to cap the other side of the ellipse. Okay, in the project, we are involved to examine which influence have TIDs on the results of direction finding systems. So we think about we used amateur radio beacons for us, two beacons here which are collected in Helsinki in Finland and the other one in Madeira. The reason for that is that we have on this radio links two ionosondes. One is in Ibro and the other one is in Julius Rue. So we have this stations send with 100 watt, 10 watt, and 1 watt, and we want to make direction finding result. So this station send with a very fixed schedule, transmit with a very fixed schedule. So we are able to store a lot of data over the time. So, for example, here's one example for the beacon OH2 Bravo, which is located in Helsinki. You'll see here on near in the middle of the path the direction, the ionoson in Julius Rue, and the locator of the direction finding system in the western part of Germany. And the question was, where can we detect TRDs? So we have, we say, a normal azimuth to the transmitter, which can you see here is 39 degrees. And we calculated then a squad different ways. The squad different way, if it's very high here, then this is an indicator of an TRD. So these values are generated over the years. We stored data over 3 years now, and we can show that there are some degradation if a TRD is coming on. On the next slide, you can see the data processing. Okay, we show you a special slide here from our BOS operation. The colleagues from ONERA sent on a frequency on 6.8 megahertz, and we used what is the best time for our field test. So we decided every time about 24 hours to store it in a database. And you can see it on this slide, the jobs for the direction finding systems, which are stored in the database. And so on this way, we are able to get back the results from the direction finding system for later analyzed. Here you can show some examples for the results. So on the right, you can see here the results of 2023, and here the values of 2024 until October on the direction link to Helsinki on this frequency here. And we saw an average value of 2.46 degrees and 2.44 degrees over this both years. Interesting is that we have the deviation is in the positive range. A lot of values are in the positive range of deviation, and only some views, some values in the negative range. Okay, so we think about the expectation from the TRD forecast capability for the ONERA system and for our side for the data direction finding missions. Philip, some words from your side?
Yes, yes, from OTHR system. So as we mentioned here, so the main objective is to optimize the availability of the system. So in that case, it could be only an alarm, and okay, we can cope with that. And actually, this is some issue that we are somehow addressing within iFurther project. So iFurther project will be presented this afternoon. So it's about a multistatic OTHR concept in which we aim to be able to select transmitters and adjust the configuration of the system. So to be sure to keep a constant capability over very wide areas. So this is the concept. So again, it could be a simple alarm and with
Yes.
which could be common with a direction finding system. So a timestamp, and as you mentioned, it could be a simple alarm with a link to a data source to get the main information on that, or it could be alert plus TID parameters. And in that case, the objective would be to, especially for OTH radar, to include this parameter in the processing, so to be able to adjust the processing to the situation. And this is something we also plan to integrate. So, again, it will be explained this afternoon by our colleague Apostolos, I don't remember his name, from HAI, in which we develop a cognitive approach for resource management. And considering this T-force and all of that, for instance, in that concept, we have a look also on every kind of external infrastructure. For instance, Yonoson. So Yonoson are not part of this project, but this kind of infrastructure could be very interesting to support the forecast capability. And but also, and I was thinking when you were speaking, actually, I think maybe direction finding could be also a very interesting system to support OTH capability, because you have real-time measurements of us, and this could be also something interesting. So. Okay, so I don't know if Stefan, if you want to add something on that.
As well, I added some points in our mission. We have online mission and also offline missions. So it's not so critical on the other side as in Philippe. The values we think that are very important thing. Values are: is there a TID or is there not a TID? Which intensity is there when the TID arrived, and so on. And these parameters are were enough for the moment. For our side of GFP, it is completely okay if we get information 3 hours in an interval from 3 hours over 24 hours. So we can store this information with our direction finding results. And so if we analyze the direction finding results, so we can also say, oh, at this time was an anomaly. We have a degradation, a very high degradation. Why is it so? So we see on the other side that is a TID arrived or a TID is present. That's the sense. Because we think that would be very helpful for us, a kind of alert system to establish after the project. In a simple way, one text line, or in an easy way, by email or whatever. So it is okay to give some main information, KP, storm parameters, timestamp, additionally information about the TID and for example weather condition. Shivan shows us some information, and the other guides here also. So for our point of view, it's completely okay to have this information after the project.
Maybe one additional point that I forgot to mention on that side. So here we mentioned to anticipate system availability. So it's from our side, but what we also expect to elaborate from this forecast capability, it's also to see to what extent a system which will be not within EU, for instance, in Russia, would be able to detect our activity and will be able to monitor an area. So anticipate system availability can be seen from our perspective, but also from the perspective of others. And this is also very important, especially for mission planning and such kind of tactical decision support. And yeah, this is another topic. So it's not only for our asset, but also to understand what are the capability of the other side.